This next problem I want to work, number 14 on the lecture examples, tells us 5.25 grams of aluminum dropped into concentrated HCl. How many liters of H2 will be produced at 23.2 degrees Celsius and 746 millimeters of mercury? So I guess they're telling us, first let's write out the equation. It's going to be aluminum plus HCl forms, now in the question it says that it's going to produce hydrogen gas, so I can go ahead and write that down, H2 plus, and if you recognize it, it's going to be a single replacement reaction because you're going to take aluminum, positive charge, hydrogen, positive charge. Aluminum's not going to be with the chlorine. Aluminum takes on a 3+ charge. Chloride has a 1- charge. So it's going to be AlCl3. And then to balance that, you got a single hydrogen, a single chloride, 2 hydrogens, 3 chlorides. So hydrogens end up in sets of 2, chlorides end up in sets of 3. So you're going to need to put a 6 on that HCl, a 3 on the hydrogen, a 2 on the aluminum chloride, and then a 2 on that aluminum. Yep, that's how you would do it. All right, now the question tells us 5.25 grams aluminum. It says concentrated HCl, so I'm going to read that as this is the excess reactant, so don't worry about it. Then it wants to know how many liters of H2. So we'll know we're finished when we find liters of H2. So stoichiometry problem. So first we got to turn given information to moles. Moles then of aluminum to moles of hydrogen, and then moles of hydrogen, we're going to need to relate that to liters. Now, if it were at STP, that'd be easy. We know that at STP, 1 mole occupies 22.4 liters. It's not at STP, it's at other conditions, so the only way to find that would be using the ideal gas law. So first, we'll do those first 2 steps. We'll go grams to moles of aluminum to moles of hydrogen, and then moles of hydrogen, that'll be one of our variables in the ideal gas law. So beginning with that 5.25 grams of aluminum times it's 1 mole of aluminum for every 26.98 grams of aluminum times then 3 moles of hydrogen for every 2 moles of aluminum. And then we're going to need to punch that in our calculator. And that comes out to be 0.291, call it 9 moles of hydrogen. And that's going to be our N value for solving PV equals nRT. Volume is clearly going to be the unknown. Pressure from the question, it's happening at 747 millimeters of mercury. Temperature is 23.2 degrees Celsius, and I think we might be flirting with the bottom of the camera shot there, but you know R is 0.0821. So then moles is the appropriate unit. Volume is going to come out in liters. Pressure, can't use millimeters of mercury. You need to convert that to atmospheres. So 747, we're going to divide that by 760. And so the pressure value is going to be just under 1 atmosphere. 747 divided by 760 gets you 0.983 atmospheres. Temperature needs to be in Kelvin, so we're going to add 273 to that. 23.2 plus 273 gets us 296.2. 296.2, and R is what R is. All right. So then if we are going to rearrange PV equals nRT, we'll divide P on over to the other side, and we end up with volume equals nRT over P. So that is going to give us, let's see, moles, so it's 0.2919 times 0.0821 times 296.2 all over 0.983. And the volume is going to come out to be, now let's think about this for just 1 second. These conditions aren't so STP, so at STP 1 mole would occupy 22.4 liters. 1 atmosphere isn't that much different than standard pressure. 296.2 isn't that much higher. So in fact, the drop in volume and the higher temperature, so it should be about 22.4 liters per mole. We're dealing with 0.3 of that. So that would be 0.2. So times 3 would get you, let's see, 6, 7. So it should come out to be about 7 liters. If it's way different than 7 liters, then I'm going to assume that I made some sort of calculator mistake. So 0.2919 times 0.0821 times 296.2 divided by 0.983 gets us, and the answer comes out to be 7.221 liters. Now, let's go back to the original problem to look for sig figs. Everything in the original problem, 5.25, 23.2, 747, all 3 sig figs. So I'm going to round that answer off. So we're going to call it 7.22 liters for our final answer of hydrogen gas.